Greetings everyone. My name is Ridham. Today my teammates and I present our work on deep reinforcement learning in cloud elasticity through offline learning and return-based scaling. We explore a hybrid system that uses both offline and online learning to create an intelligent autoscaler that improves performance, reduce costs, and makes safe scaling decisions. So now let's see the introduction. As cloud native container based architectures become mainstream, Kubernetes is the standard for application orchestration, yet its autoscaling lacks true adaptability. While traditional RL methods can manage these complexities, they require long training periods and risk disruptive live services. The risk disrupting lives, the challenges include managing a high dimensional state space and dealing with delayed performance feedback after scaling actions. Now let's see the overview of the paper. This paper addresses the limitations of traditional autoscaling in Kubernetes, which rely on static thresholds and struggle with fluctuating workloads. Our approach, RBS CQL, combines deep reinforcement learning with offline pre-training and a return-based scaling strategy. By integrating DDQN for real-time adaptation with conservative Q learning from historical data, our system focuses on long-term gains rather than short-term fixes. So the problem statement of our research paper is we have seen traditional threshold-based scaling is inflexible, often resulting in suboptimal performance under unpredictable workloads. Additionally, training on RL agent in production is both costly and risky, potentially disrupting services. This situation creates a need for a smarter auto-scaling solution that learns from historical data to anticipate needs while avoiding live training pitfalls. So the objective of our research paper is to develop an intelligent autoscaler using deep reinforcement learning to determine optimal scaling strategies. By harnessing offline data from system logs, we aim to speed up training and avoid live disruptions. The approach uses return-based scaling for long-term decision making and conservative Q-learning for safe offline learning, validated in a realistic Kubernetes and Cassandra setup. The proposed system we used is RBS CQL. It is a hybrid model that merges offline pre-training with online refinement. It starts with conservative Q learning on historical data to establish a safe baseline, then uses double DQN for fine-tuning in real time. The inclusion of return-based scaling ensures that the agent prioritizes long-term rewards, leading to efficient and stable scaling decisions. Now, Hardik will continue ahead with the architecture.
Hello, my name is Hardik, and now I'll continue with the PPT. So our next slide is architecture overview. So our architecture integrates several open source technologies. Kubernetes manages the application pods. Cassandra handles data storage, and Prometheus and Grafana monitor and visualize system metrics. We use YCSB to simulate realistic workloads while the DRL agent continuously evaluates these metrics to make informed horizontal scaling decisions. Now let's look at deep reinforcement learning agent. The agent processes key system metrics like CPU, usage, memory, latency, and throughput to decide whether to add, remove, or maintain pods. Its reward function is designed to balance performance with cost efficiency. Training begins offline using conservative Q learning and transitions to online fine tuning with DDQN, ensuring rapid adaptation in live conditions. Now let's have a look at conservative Q learning. So conservative Q learning is essential for offline training using historical data to safely pre-train the agent. It penalizes actions that are rarely seen and employs scale divergence regularization to keep the policy close to the data distribution. This approach results in a robust safe policy that minimizes the risks associated with live exploration. Return-based scaling or RBS. Standard queue learning often focuses on short-term rewards, leading to unstable scaling decisions. RBS shifts the focus to future cumulative rewards. training the agent to consider the long-term impact of its actions. This results in more stable and efficient scaling, especially during early training phases when decisions are critical. Our experimental setup consists of Kubernetes cluster running Cassandra with Prometheus monitoring and Grafana visualizing key metrics. YCSV is used to simulate varying workload conditions. We evaluated the system on latency, resource utilization, the speed of scaling responses, and overall cost efficiency, ensuring a through reassessment of our approach. Now let's have a look at RBS SQL versus DDQN. Evaluation shows that RBS SQL significantly outperforms a standard DDQN based autoscaler. It improves early learning by over 10%, converges faster, and maintains stable performance under fluctuating workloads, all while achieving best cost efficiency by minimizing unnecessary resource allocation. So now my partner Vivan Jain will take over.
Okay, so basically, what we have done in this implementation is built a reinforcement learning system that can automatically decide whether to scale cloud servers up or down based on the CPU load. To test this idea, we created a simulated cloud environment where the agent gets to choose whether to increase or decrease or keep the number of running instances as it observes the current system state. The state is pretty simple. It includes how many instances are running and what the current CPU load is. Uh, the environment gives the reward depending on how good that action was in keeping the system balanced, like avoiding overloading or wasting resources. Now, to make those decisions, we built a deep queue network, or DQN for short. This is basically a neural network that takes the current state as input and predicts what the expected future reward would be for each possible action. Then, based on these predicted values, the agent decides which action to pick. In the beginning, to let the agent explore different options and learn from them, it sometimes chooses the random actions. This is called exploration. As it starts getting better over time, it shifts to exploitation, meaning it chooses action it knows will give better results based on past experiences. To help the agent learn more efficiently, we also use something called a replay buffer. Think of this as a memory box where the agent stores its past experiences, what it did, what happened next, and what reward it got. Instead of learning from the most recent steps, it picks random experiences from this box to train itself. This makes the learning process more stable and diverse because it's not just repeating patterns but mixing up situations it faced earlier too. The agent uses this experiences to update its knowledge about which actions are good and which ones aren't. As the agent trains, it keeps interacting with the environment episode by episode. In each episode, it starts fresh by making decisions, collect rewards, and stores those experiences. After every step, it updates its neural network based on random past experiences from the buffer. Along with this, it slowly reduces the exploration rate, epsilon, meaning over time it depends more on what it has learned instead of guessing randomly. The total reward it gets in each episode is saved so we can track whether it's improving as the episodes go by. So now my partner Aditya Kakkar will lead us through the results and the conclusion of the experiment.
Hi, my name is Aditya and I'll explain the output and graph explanation. Now, if you look at the output on the terminal when you run the program, you will see it shows the episode number, the total reward collected in that episode, and the current epsilon value. In the beginning, the reward might be random or low because the agent is still learning. But as the training continues, the rewards start increasing and becoming more consistent. After all the episodes are done, we get a graph where the x-axis shows the episode number and the y-axis shows the total reward. This graph is super helpful because it visually shows whether the agent is actually learning to manage the cloud instances better. If the graph tends upwards or stabilizes at a high reward, it means our model has worked well. Results and performance. Our results indicate that the RBS CQL accelerates learning and maintains a stable scaling policy. Compared to the traditional methods, the system intelligently adjusts resources only when needed, ensuring low latency and high throughput, and achieves an optimal balance between performance and cost, validating our hybrid approach. So this is the conclusion and future work. In conclusion, RBS CQL offers a smart adaptive solution to the limitations of traditional autoscaling in cloud environments. It successfully combines offline pre-training with cautious online learning to manage dynamic workloads without disrupting services. Future work could explore multi-agent collaboration, predictive scaling, and multi-cloud implementations to further enhance its capabilities. Now, the Q&A and references. Thank you for your attention. Our work builds on the insights from the IEEE Cloud 2023 paper, Newer IPS 2020, on conservative Q-learning, and key technologies like Kubernetes, Prometheus, Grafana, and YCSB. We look forward to your feedback. Thank you so much.